discuss the nature of bonding in metal carbonyls. Oh my God, how do metal carbonyls form bond? What are metal carbonyls? If a metal atom or a metal ion combines with carbon monoxide ligand, then what you get is a metal carbonyl. Okay. And what happens is this. I mean, this is a very formal routine answer you can see. You can take a look, no doubt. I'll explain the same answer. If you want a written answer, this is the answer. You can just write down with grammar, but the explanation comes here. Let me say this for you. Very important question, very useful question. What happens is this. First of all, please remember metal carbonyl. In metal carbonyl, carbon monoxide is a very powerful, it's a strong field ligand. Because it is a strong field ligand, you find that all the metal carbonyls are low spin complexes. So whenever there is a distinction possible, number one, CO is a strong field ligand. Hence, all metal carbonyls are low spin complexes. So they cause pairing of electrons. Yes, if there is a possibility, they always cause a pairing of electrons. Let us, for example, take a case of the very famous NiCO4 tetracarbonyl nickel. Now, oxidation number of nickel in this case is 0. That means it has electronic configuration argon 3d8 4s2. If you look at the ground state configuration, I'm just drawing boxes so that I might be able to use them later, and the later has come now. This is ground state. 1, 2, 3, 4, 5, 6, 7, 8, 3d8, 4s2. This is ground state. But since carbon monoxide is a strong field ligand, it is going to push the electrons in, and you find 1, 2, 3, 4, 5, 6, 7, and you find now some mess happening around. What happens is that these electrons get pushed. This electron is pushed here, they both are pushed here, and this is what you get. Okay, wow. So is this the excited state which happens during bonding? Yes, this is that excited state which happens during bonding. This is incomplex. So since these electrons are pushed in, it becomes an inner orbital complex. These are now available, so hybridization now becomes sp3, etc., etc., which is fine. Carbon monoxide also has donated one lone pair each. So that means nickel itself, which had oxidation number 0, now has 4 electrons from carbon monoxide, and that makes nickel very uneasy. Why? So many electrons, so many electrons which nickel has gained, and nickel being a metal does not much appreciate electrons. Metals are electron donors, right? They don't like to get many electrons. It has got it. Because of greed, it can't leave it, but because of its own nature, it's not also very happy about it. What do they do? Now there comes the very special part of bonding in metal complex. Now you are about to witness what is called as synergic bonding or back bonding. Wow, synergic or back bonding, what are they? Observe very carefully, I am going to erase this. D orbitals are now filled in NiCO4. At least there are electron pairs in d orbitals. Yes, lone pairs also, if you may dare calling them that way. Yes, indeed. What happens? What happens is this. Watch carefully. As carbon monoxide donates a lone pair to nickel, fanciful CO, CO, CO and CO, very glamorous, you can say, diagram. What you find now is nickel, because it is now very electron rich, tries to give back electrons. And how does it give back? Let me just demonstrate with one diagram. This is a d orbital of nickel. Just don't look at these three carbon monoxides, just look at this and this. Fine. And you have carbon, you have a pi bond also here, right? Like this. So forget this for the time being. I won't be able to erase it, it would become very messy. But just let's assume that there are only two bonds here, and the third bond I have shown using the orbitals. Okay. Now what happens is, if this bond, if this electron cloud gets pushed, how? It gets pushed on this one. If this pi bond breaks, if the electron is pushed on O atom, what happens? This empty p orbital, this empty p orbital of carbon now can form a pi bond with this d orbital. This is d pi, p pi back bonding. If you are talking in terms of valence bond theory, this is d pi, p pi back bonding. And because of this, this doesn't happen only with one, 2, 3, 4, it happens with all. And because of that, some electron density from nickel is taken away by carbon monoxide, and nickel becomes very relieved and very happy. And the bonds with nickel also become stronger, because instead of just one sigma bond, you now also have a pi bond. This is in terms of valence bond theory. If you want to discuss the same thing in terms of MO theory, there is also a very fancy word. We call it synergic bonding. How do we say this? Idea is the same. We say there is a metal atom, yes, and there is carbon monoxide, yes. If you find this diagram difficult, I would suggest that you draw it with me so that you don't find it difficult anymore. Let's draw it together. I have metal M, yeah, and this metal M has made a bond with carbon monoxide. Yes, it has made a bond with carbon monoxide. This bond is shown here. It is this bond, which is being shown by an arrow here. Can you see that? Okay. Just for the sake of cleanliness, let me not highlight this. Just let me make a line and write this so-called coordinate bond or a covalent bond. Now, metal M has empty d orbitals. Of course it does. Like butterfly wings, you have these stupid empty d orbitals. And carbon monoxide, now these are bonding orbitals, fine, but there also would be certain empty anti-bonding orbitals. Yeah, there are always. So let's say that carbon monoxide also has certain empty anti-bonding orbitals. It does. And these anti-bonding, see, this is one anti-bonding orbital. And all this is a sigma, this portion is a sigma bond, this is a lone pair, I am just not mentioning them. The blue ones are 4 lobes of pi star CO. What is pi star CO? It is an anti-bonding orbital. Are there 4 orbitals? No, there is only one orbital which has 4 lobes like this. And this anti-bonding orbital, when it forms a kind of bond with this, you find that this orbital was anti-bonding for a bond between this carbon and this oxygen. And now when it overlaps with metal, this becomes a bonding orbital between metal and carbon. Yes, indeed. And because it was anti-bonding between C and O, you find that CO bond order decreases and metal-carbon bond order increases. That's dirty. That's clean. Just listen to it twice or thrice, you'll get the idea. It's not a difficult idea, just a fresh and new idea. And this bonding is called synergic bonding. It is the same kind of thing. It is very much same kind of thing, just that this is an MO explanation with a very fashionable new name, synergic bonding. And what we talked about was a classical valence bond theory name, which is d pi p pi back bonding. Either way, it's fancy, it's good, and it's useful. I hope you understand this.